All right, good morning. So today's class, in lieu of us just getting back from a long break, the goal of it is just going to be to review sort of everything. So I'm going to go through our 4 past exit slips. You've already got your scores for them if you've done them. And you already sort of know like where you were about before break. But we just want to make sure everyone's on the same page and sort of get back into it. Just by going through all 4 of our exit slips. So hopefully it'll help those of you who are unsure feel better about it. And those of you who are lost, sort of get yourself a place to grab onto before we go back into full swing of school. I will say it is a hard unit. You guys are doing a really good job of learning at home. I'm seeing some really good thinking and some clear learning processes happening. So we're doing really good. So this is our April 2nd exit slip. This is a pretty straightforward one, I thought. Most of you did pretty good on it. So we had rectangular yard was enclosed by 100 meters of fencing. The table shows some possible values for the length and the width of the yard. All right. So we have length and width and area. And the questions here I know appear on different pages. So I'll just go ahead to the next page. I print out the PDFs, so I actually got to see what you guys see if you print out these forms. And they're very bulky, I realized. They don't print very nicely. I don't really have a way to change that, but that just is what it is. So write the values that like A and B and C must have. So basically, a very simple looking problem got turned complicated. So anyway, we have rectangles. All right, and there's 100 meters of fencing enclosing it. So basically we have length and width and length and width. So basically we know that all of this has to add up to get you 100. It's 100 meters of fence. So basically, 2 lengths and 2 widths got me 100 meters of fencing. Or some of you could think about, well, half the perimeter, 1 length and 1 width could be 50. So length and width add to get me 50. And we notice that in all these pairs, 10 and 40 get me 50. 20 and 30 get me 50. 25 and 25 get me 50. So I can think plus gets me 50. Plus gets me 50. Plus gets me 50. And then, well, how do we get the area? Well, the area of a square is just length times width. So, okay, 10 times 40 was 400. Well, 20 times 30 got me 600, so that's what A is, 600. And then, okay, 25 times 25 is 625, 35 times 15 is 525. Well, all right, if my length is 40, what does my width then have to be? Well, if my length is 40, I know that, let's see, well, 2L plus 2W is 100, so 2 times 40 plus 2 widths equals 100. So 80 plus 2W is 100. Well, so I know that my 2 widths have to be 20, so width has to be just 10. Or if you're thinking along the lines of like, well, length plus width gets me 50, 40 plus what gets me 50, that has to be 10. All right, so B's got to be 10. And also, like, length and width could be flip-flopped. Like, length 10, width 40, that just flip-flops. And again, 40 times 10 gets me 400, which is where that comes from. And then D, E, and F, you have to come up with your own pair. So I know a lot of people came up with, like, 45 and 5, or there were many other ones. Basically, any 2 numbers that added to get you 50, and then multiply them together. 45 times 5 is, like, 225, maybe? Yeah, 225. Then another combination that was, let's see, people like 24 and 1. I'm trying to think of what other people did. This one actually graded more than an hour ago, so I don't remember exactly what people did. They could have done like 22 and 28, or any 2 numbers that added to get you 50 here, and then just multiply them together over there. All right. So that's pretty much it for that whole cool down 4.2. I'll try. You could have also done like, I don't know, like 22 and 28. And then whatever 22 times 28 is. which, let's see, okay, 30 times 22 is 660, minus 44, were they like 616 or something? I don't know. That sounds about right. So yeah, you could have done those, any combination pretty much that adds to 50, and then multiply those two numbers together. There's the first one. Not too bad. Get rid of that. So many pages. Next one. All right. Luckily, it automatically collects email addresses when I remember to do it. So let's see. How does the number of squares change with each step? So really, the goal with a lot of these things, especially now that we're done 4 lessons, the goal with a lot of these things with quadratic relationships, quadratics relate to something being squared, which a lot of you did really good on in the April 7th exit slip. It refers to something being squared. Like square, quad has 4 sides. Quadrangle is a square. Basically, they're all the same word. So quadratic, you want to think something being squared. So where does x squared fit into this? Or where does x times x fit in? That's your real goal, is to figure out where does that all fit in. And the x is really our step number. So you want to think about where do I see an x? Where do I see that x? And where do I see an x here? And where do I see an x here? So a lot of you are giving verbal descriptions, and like that's good to be aware of, and I gave you full credit for those, but really we want to move away from verbal and write them more as formulas or expressions. That's our real goal. So we can talk about them in formulas, but really we can talk about them in words, but we want them as formulas. So really here I notice that I have a 1 by 2, and here I have a 2 by 3, and here I have a 3 by 4. So what I notice is if I have step number x, I have an x by 1, and I really should have done n, but I have an x by x plus 1 rectangle. All right, so those of you who said we're adding a row and we're adding a column, like yes, but really our step is increasing, and our step is our width and our length. So really, because we want to think about things more in terms of that. So you have an x by 1 rectangle. So how many squares are there in step 10? I don't know, but we have an x by x plus 1, and if x is 10, we have 10 times 10 plus 1, which is 10 times 11, which is 110. All right, so I really want to start seeing all these things in terms of like, all right, where is the x? Or I'll change it to n. Where is the step number? That's like our main, like we want to find that in our drawing because that'll help us write a formula. All right. So here, where's our step number down here? Well, let's see. Step 0's got nothing. Step 1 has 1 row of 4. Step 2 has 2 rows of 4. Step 3 has 3 rows of 4. All right, so this one, turns out this one's not actually quadratic. We can tell because it's adding 4. That's linear. So really, our rule there is just 4n, or just 4 times the step number of 4, which is just 16. All right. But almost, this one is not quadratic, so I'm going to be really careful that we're not just assuming quadratic. I just want to notice that that's where quadratic's happening. We're changing both dimensions is where quadratic comes from up here. But down here, the base or the width is the same. The width is 4. It's the height that's changing because the height is the step number. All right. Right rule to describe that. A lot of you still weren't writing it in formulas, which is all right, but we want to make sure we're really getting close to, all right, y is the number of dots. So y equals, what about the nth step? Well, it's just, let's see, at step 1 we had 4, and at 2 we had 8, and at 3 we had 12. So it's really just 4 times the step number. how many dots will there be on the fourth step here? This one's a little bit weirder. We got these 2 dots down here. You have 2 dots here again, but we have a 1 in the middle. You have 2 more down here, and then we have 2 by 2 now. Get rid of that X, sorry. And then over here we have 2 dots still, but we have a 3 by 3. So anything staying the same, you want, there's 2 plus something, because there's always that 2. And what's that something in the middle? It's 1 by 1, it's 2 by 2, it's 3 by 3. Oh, it's an X by X. It's an X by X square. N, sorry, I'll do N. It's an N by N square. It's an N by N square. So it's 2 plus N times N, or 2 plus N squared. Oh, I'm writing computer lingo, what the heck? N squared. Sorry, it's like 10 o'clock at night. So, bear with me. All right, so then write a rule. We already wrote the rule. Fourth step. Well, okay, sometimes it's helpful to write the rule before we find out what there actually is in each step. I like to figure out what's going on here, especially me as a more mathematical mindset. I'm geared toward teaching this. So now that we know what the rule is, we can say, well, if n equals 4, 2 plus 4 squared is 2 plus 16, which is 18. And that one, we did pretty good on that one. We did pretty good on a lot of this. A lot of you are doing great. You really want to make sure that those of you who are struggling are taking this as your new, like, all right, we've had 10 days off, let's start over again. Let's go through everything we've already done. Okay, because I know who you are and you know who you are. Okay, so we got that rule, y equals 2 plus n squared. All right, and n is just in general, like on some random step, I can figure out how many dots I have. So n is like your variable. Don't get confused by the nth. That just means it's some number step. So it could be like, if it's the 9th step, it would be 2 plus 9 squared. Some of you were doing that in your explanations. You were like, well, if n is 9 or if n is 10, like, well, n can be anything. But I gave you guys a lot of credit for what you were doing because you had the right ideas. If I can tell you have the right idea, it's just not down properly, I'm pretty much going to give you credit for it because that's the best we can do here, right? Okay, so there's that. Nth step. Well, again, we're looking for that n. Step number is 3. We're looking for that n in our drawing. It's an n by n. N is 2. N is 2. N by n. Let's see. Oh, that's the first page. That was it for 4-6. Awesome. Okay. April 7th. Let's see. So this one, what do you understand about the quadratic growth? This was the first day we actually talked about the word quadratic. So I really wanted to make sure here, the goal was that when we talked about quadratic, you understood what you were looking for. So quadratic basically implies that something is being squared. And this is a terrible definition, but basically something is being multiplied by itself. And if you put that in your definition, basically you give you credit for it. All right. So that's basically what we're looking for with quadratic growth. It has an x squared in it. It's not 2 to the x, because that's exponential. That's exponential because the variable is the exponent. Quadratic means the exponent is 2. All right. So that's basically our main difference. Quadratic means the exponent's 2. Exponential means exponent is x. Exponent is the variable. These are like doubling and tripling, quadrupling problems. Yeah. Okay. And if you look up the definition of quadratic, it's basically just going to say it involves the second and no higher power. It's like something squared. Not cubed, not to the 4th power, squared only. So how's that one? We're just looking for that pretty much. And that's for now is all we're going to talk about pretty much. Which function's quadratic? Well, it's the one where something's being squared. X squared. That 3 to the x is exponential. 4x is just linear. All right. So we should have gotten C for that one. And again, you've already gotten the correct answers for these or my feedback for it. So please make sure you're listening, understanding what you did wrong. Or like, oh, now I understand it. Cool. That's the goal. Please reach out with more questions. Don't just say, I don't know, or don't respond with like, I can't do this. You can do it. Just make sure you're reaching out so I know what you're having trouble with, because I know we can make it work. Okay. So, all right, select, oh yeah, the select alls always look terrible on this printout. So select all the expressions that represent the number of squares at the nth step. So this hint was basically like, hey, in your equation, when you let n equals 2, you should get 3. And when n equals 3, you should get 8. So you could have just plugged in all the numbers and seen which ones worked, which is really what I was expecting a lot of you to do. I think some of you probably did. Even if you got just one of the rules, like, you're good. Like, if you got any one of the rules, like, I don't really find any problems. So basically, we really want to see where these rules come from and where you can see all these rules above. This is a great problem for that. Let's see. Okay, so there's our drawing. Let's start with the first options first. We'll just fold the paper. Okay, so step 1's got nothing. So if I let n be 1, I should get 0. So this one, if I let n be 1, I get 2, which is not right. All right, this means something's being squared and we're adding something else to it. Well, if I square 1 and add 1, I do not get 0, so it doesn't work. This one, n squared minus 1, I do get 0, so that one works. And let's see if it works for 2. If I let n be 2, I get 3. So that also seems to work. And pretty much if it works for 2, it's almost guaranteed to work for all of them. The quadratics, you really should try 3 because there is some crazy chance it'll work for 2 but not for a third one. So if n equals 3, and I can prove that later, but I'm not going to. So if n equals 3, let's see, 3 squared minus 1 is 8. So it works for 3, it's going to work for all of them. All right. So let's see, where do we see n squared plus minus 1 up here? Well, let's see. I know that 1 squared is 1, so a 1 by 1 square, and then minus a 1 by 1 square. That gives me 0. All right. So that's a 1 by 1 minus a 1. Now for a 2 by 2, I see I have a 2 here, which is n, and a 2 here, which is n. Then they sort of cut out this bottom one. So that's kind of like the n squared minus the 1. And over here, I see a 3, which is n, by 3, which is n. And then again, we cut off 1, which is again n squared minus 1. So that's an easy one for me to see personally. I can see that pretty well. And there's some down here that are a little bit weirder to see, but they're still there. All right, n squared minus n. So let's see, does that work? If n is 1, I get 0, which works, okay. If n is 2, I get 2, which is not what I'm supposed to get. So this one does not work. Okay, so 2 worked, 1 does not, and 3 doesn't work. So if you only tried n equals 1, you would have found that this one works. But even if I try 3, 3 squared minus 3 is 6, which is not what I wanted. So that would basically look like if I did an n by n, and then like got rid of a whole row. Or if I did a 2 by 2, and then got rid of a whole step. Or a 3 by 3, and then got rid of a whole step. That's what that would look like. Because n squared minus that down there is n. All right, that's not what happened there. Now n squared plus n, let's see if that works. Let's see, 1 and 1. That gives us 2, which is not what we wanted. It does not work. This one would basically be like a 1 by 1 plus 1. And then a 2 by 2 plus 2. And if n equals 3, you have a 3 by 3 plus 3. Oh, jeez. So we'd have like something like that, if that was our pattern. But this one definitely does not work either. All right, this is one of those ones where I really just too many options. Am I right? So let's fold the paper down and try option, whatever we're on now. 5, is it? Good grief. Option 5. N times n minus 1. Well, if we notice, n times n is just n squared minus 1, which is what we already decided. So that one is going to work. Spoilers. But let's just say 1 times 1 is 1, minus 1 equals 0, which is good. 2 times 2 minus 1, that's 4 minus 1 gives me 3. Works. 3 times 3 is 9, minus 1 is 8. It works. So that's what we wanted. So option 5 works. Option 6. That looks weird. Some of you might have just said no because it looks scary. I encourage you not to do that. I know all about these things, and I know how to make scary things turn into easy things. So let's plug in our numbers. Let's just say, okay, n is 1. Let's see, 1 times 0 plus 1 minus 1. Seriously, dude? Okay, 0 plus 1 minus 1 is 0. That worked. Let's try 2. Do it pink. 2. 2 times 2 minus 1 plus 2 minus 1. Okay, so 2 times 1 plus 2 minus 1. So 2 plus 2 is 4 minus 1 is 3. That also works. Good grief. Let's see if 3 works. It does. So 3 times 3 minus 1 plus 3 minus 1. And I'm just letting n be my step number. So 3 times 2 plus 3 minus 1. So 6 plus 3 is 9, minus 1 is 8. So that works as well. So I really want to see where the heck does this pattern fit in up there? And I'm going to actually redraw it right here. Bear with me. So n equals 1, I got nothing. N equals 2, I have this. And n equals 3, I have this beautiful thing right here, which is a... Dang, that was good. Okay. Which is the, yeah. So I notice I have a 1 missing here, which is maybe where that comes into play. But let's see where this n times n minus 1 comes in. When I see n times n minus 1, I want to think about like a rectangle with area. So I'm thinking about like that's n and like that's n minus 1 side lengths. So in step 3, that'd be like a 3 by 2. So that's kind of this left half here. That's my n times n minus 1. And then this stuff right here, what we added in, this is 2, so that's really n minus 1. So then we're adding in an n minus 1. Or you could say we're adding in another row, another n, and then subtracting that 1. And what it looks like here is the same kind of deal. This right here is my n times n minus 1, because it's 2 by 1. And we added over here n minus 1, because n is 2, and we added 1 less than that. So we added 2, or say we added 2 and got rid of 1. I know it's weird. I'm never going to make you come up with a formula that looks like this, as long as you can come up with something that looks like this. But you will see much later in the year, maybe in May or June, how to realize that this does turn into that up there. I'm going to show you now. It's like, it's late, but we can do it. So n times n minus 1 plus n minus 1. Distributive property. Boom, boom. N squared minus n plus n minus 1. Minus n plus n is 0. So that leaves us with an n squared and a minus 1. Boom. That turns into that. Pretty cool, right? No. All right, next problem. Whatever, fine. I think it's cool. And so do some of you. And I appreciate those of you who think it's cool. And I can't hear you. All right, n minus 1 times n plus 1. I'll draw the picture back here. Okay, the n equals 1 step is boring. I'll show you n equals 2 and n equals 3. So n equals 2. This one's actually going to be pretty cool to see as a drawing because it involves rearranging. And those of you who are more geometrically minded will appreciate the rearranging aspect of this one. We don't know how to multiply this out yet, but you will in June. So basically what we see here is, all right, where does the n minus 1 times n plus 1 come from? So it's going to come from me taking this and putting it up there and turning it into a line, which is 3 by 1. And that 3 is n plus 1, and that 1 is n minus 1. And this one down here, we're going to take this 2 and we're going to push it up over there. So we're going to make it a 4 by 2. And 4, by golly, is n plus 1. And 2, by golly, is n minus 1 here. Because here, n is 3. And here, n is 2. So that's pretty cool. All right. Stand with me. Again, as long as you can write option 2, option 7 is just like, hey, look, that worked. And if you try the math, it works. Trust me. Or you just do it yourself. It's pretty easy math. Just let n be all those numbers, and it should get you 0, should get you 3, and it should get you 8. Okay. So side length of the large square is x. This one you guys did super good on. I got a lot of pretty good answers here. Basically, side length is x. So my area is x squared, and then I'm subtracting 1, 2, 3, 4 1 by 1s. So x squared minus 4, or x squared minus 1 minus 1 minus 1 minus 1, or x squared minus 4 1 squareds. Doesn't matter how you write it. It's all good. This is the best way. Doesn't matter. All right, because I had a square with a side length of x. Here, we have squares with the side length of x again. So it's an x by x. X by x is x squared. 2 by 2 is 4. 2 by 2 is 4. So really that's because we're writing x squared plus 4 plus 4, which is fine. It's totally good way to write it. But again, we can combine our like terms and write 2x squareds plus 8. And remember, we don't know what x is, so we can't really evaluate it. But you did good if you got those ones, all right? And again, make sure you understand what we're writing. Please make sure you're reaching out, saying, Mr. Roboto, problem 6, or just say, hey, at that movie at the 27th minute, because I was still watching at that point, I had a question about this. Just shoot me an email. I'm almost always here. All right. It's a long video. It's okay. Your assignment will be short-ish today. How many squares will be in step 4? All right, so here I notice, let's see, again, we want to look for quadratics, which is something being squared. Where is the step number in these patterns? So where do I see a 1? I see a 1 here and a 1 here. Where's the 2? Okay, I see a 2 here, and I see a 2 by 2. I see 3, and I see 3 by 3. Okay. So it looks like I got 3 times 3 plus 3 here. I got 2 times 2 plus 2 here. So it looks like step 4 is going to be 4 times 4 plus 4, which is just 20. You guys are good with that one. Select the correct function. There was only one here, I'm pretty sure. And that, let's see, if we looked at the above, my 4 times 4 plus 4, that's really the same as 4 squared plus 4. So really, I got n squared plus n, which is, nope, that was wrong, sorry. N squared plus n, it's C. Yeah, sorry, that was bad Roboto. All right, because again, n squared, that's where we had that square with side length n. And then that's just like a row of n boxes. So in step 3, we had a 3. In step 2, we had a 2. And in step 1, we had a 1. And then the n squared is we had a 1 by 1, and a 2 by 2, and a 3 by 3. Oh, that one's done. All right, this is the lesson. Basically, the goal of this lesson was to show that exponential grows faster than quadratic and linear, always, pretty much. So basically, the answer to Cormac's question at the end of that lesson was there were none. except decay values. I gave you credit for none because I said none a lot in the video. I also gave you credit for decay values, so if B was more than 0 but less than 1, and really some of you tricksters said 1, and technically 1 also worked, so really you could have written that. So I gave you credit for 1, I gave you credit for anything between 0 and 1, I gave you credit for none. I did not give you credit for anything else. But basically, the goal of this is to think that exponential always grows faster. So is the quadratic going to be greater than the exponential? And the answer is no, because that grows faster. And these guys seem to really understand that, or at least be able to repeat that to me in the lesson, or at least in my exit that I read. Same with Kristen's problem. Like, look, 5x squared, these are big numbers. That's always going to be bigger, right? Well, no, because at approximately, I'm going to mess up the number, it's approximately 7.4952 or something. 2 to the x is bigger than 5x squared. I don't know, someone did the math for me and it was probably a better answer than that. But basically, at some number, these get larger than that. All right, and the graph, if I sketch this graph in black, which I probably shouldn't, but I'm going to anyway, and I sketch that in red, it's going to look like this. It's going to look like, this black one's going to be like that. And this pink one, is that pink or red? I don't know. That red one is going to be like this. And that exponential has that characteristic, like it goes straight to heaven. It goes straight up in the air. Whereas the quadratic is more gradual. It doesn't appear gradual, but it is gradual. More gradual. All right. Same down here, provide some integer. You had to give me something bigger than 8. Now, I know, some of you gave me really small numbers. And technically, if you put in like x is 0.01, it also works. But it's not like, that doesn't tell us like the long-term behavior of the graph, so I didn't like that answer so much. We wanted to pick numbers like bigger than 1s. Like eventually as we keep going, what happens? Because if I zoom in really, really close on this graph here, what happens if I do that? If I let like this be pink and that be red, what really happens is at first, the exponential, remember, exponential graphs really, their y-intercept is 1. So the exponential graph in red starts at 1. And the pink graph, the quadratic, actually starts at 0. So really what happens is the pink starts lower and gets higher and goes up. And the red graph starts here, gets low, but then gets higher again. So they really cross twice. And if you zoom in close enough, it happens. But these cross at like some super, super early point, like 0.03 or something. Or 0.3, or I don't know. They cross at some point early. So yeah. The main goal is seeing the long-term behavior. So the goal is exponential increases faster, eventually. It will. I still have a couple left. These ones are more review-ish. Again, seeing where do I see the n? Where do I see the step number? Props to you if you are still watching this video, because I know some of your lazier peers will have already turned off the video, which is fine. That means that they're not going to get the bonus question, and only you will get the bonus question. So, basically, here's the bonus question. Yeah, that's the answer to it. Anyway, it's just a fun bonus for me. Okay, so yes. So I'm gonna email alerts. Okay, so I want to see, where do I see the step number in all of these shapes? My step number is 1. I see a 1 here. My step number is 2. I see a 2 here and a 2 here. My step number is 3. I see a 3 here and a 3 here. So my rectangle So I see a rectangle. So it's a 1 by 2, and a 2 by 3, and a 3 by 4. So that looks to me like an n by an n plus 1. And then what am I adding up to the top? There's nothing on top here. There's 1 on top here, and there's 2 on top here. So I'm adding an n minus 1 there. So what do I have to figure out? I figure out what's the area of the shape in step 4. I should figure out the area here. Oh, dang it. That's easy. Okay. So, well, I could use my rule. Or I could think, well, all right, in step 4, I'll have, let's see, it'll be 4 tall, it'll be 5 wide, and there'll be 3 on the top. So, let's see, 4 by 5 is 23. 23. All right, so that is my answer there. And I'll use my rule on the back, hopefully. Yes, okay. So then, what is the area of the shape in step n? Yeah, let's use our rule. I came up with n times n plus 1 plus n minus 1. So I came up with that. Because that was my rectangle height. That was my rectangle width. And that was the top row. So this one definitely works. Let's see. There's all that apply. This is the one where I made it only you could choose one. There's actually 2 that worked though. So yes, that one works. And also, let's see which other one works. I'm going to distribute this to figure it out because I can't do the math right now. N squared plus n minus 1. So n squared plus 2n minus 1 also works. So it's 2, and also 3 works. And just real quick, I'll see, where do I see the n squared plus 2n minus 1 up there? So let's see, in step 1, I have just 2 blocks. In step 2, I have a 3 by 2 and 1 up top. And in step 3, I have a 3 by 4. And 2 on top. So where do I see n squared plus 2n minus 1? So I'll put the n squared in pink where I see that. So I see n squared is a 1 by 1. So there's a 1 by 1 there. Here n squared is 2 by 2. So there's my 2 by 2. And here n squared is 3 by 3. So I'll do that 3 by 3. Okay. So then, let's see, where do I see the 2n minus 1 being added on? The 2n minus 1 being added on, well, let's see. For 1, I got a 1 and a 1 that they then took off that one. For here, my n is 2, so they added a 2 and a 2, but they got rid of that one. So that's 2 n's minus 1. And here, n is 3, so I got a 3 and a 1, 2, 3, but they got rid of that one. That's where I see that. All right, and the other ones don't work. Listen, great job getting through this whole video. It's been 38 minutes. This is way too long for me to be talking at you. But great job, and you have the bonus question if you stayed with me. So yay, good job.